there is a teaspoon in your kitchen drawer. Tonight, I am going to fill it with something that weighs 6 billion tons. Not a figure of speech. 6 billion tons, that is, matter taken from the core of the object we are going down to meet, in the bowl of a spoon you could hold between 2 fingers. To put that in something you can picture, every human being alive on this planet, all 8 billion of us, weighs about 400 million tons altogether. That one spoonful would outweigh the entire human species. 15 times over. Now let me settle that before we go anywhere, because it sounds alarming, and it is not. The nearest object that could fill that spoon is 400 light years away, about 600,000 times further from you than the sun. Nothing in tonight's story can reach you, disturb you, or change anything about the room you are lying in. We are not visiting a threat tonight. We are visiting a curiosity from a very safe distance, and we are going to take our time getting there. Welcome to Calm Science for Sleep, where the universe is explained slowly and nothing is ever in a hurry. Tonight we walk down a staircase. Not one made of stone, the theme, one made of heaviness. At every step, the thing in the spoon gets denser. We start in your kitchen, and we do not stop until we reach the densest place that matter is allowed to exist. So settle in. Let your shoulders drop. Let the day loosen its grip. Take one slow breath in and let it out. The first step is already in the drawer. So let us start there. In a drawer, you have opened 10,000 times without thinking. Fill the spoon with water, right to the brim, and you are holding about 5 grams. The weight of a grape. A folded banknote. Almost nothing at all. That is the top step of our staircase, and I want you to keep hold of it, because we are going to carry this same spoon all the way down. And before the first step, there is one fact about that water you need, because the whole staircase rests on it. Water is made of atoms. So is the spoon. So are you. And atoms are almost entirely empty. If you scaled a single atom up until its nucleus was a marble, sitting in the center of a football stadium, the electrons would be drifting somewhere out past the highest row of seats. Everything in between is nothing. Not thin, not rarefied. Nothing. Let me show you what that emptiness is worth, because it is the whole of tonight's story in one image. You are made of atoms. Every one of them is more than 99.9% empty space. So what would you weigh if the emptiness were taken out? Not less. Exactly the same. You would weigh what you weigh right now. The scales would not change by a gram. What would change is the size. Compressed to the density we are heading towards tonight, an entire adult human being would occupy a cube about 5/1000ths of a millimeter on each side. That is smaller than a single red blood cell. Smaller than most bacteria. You would need a good microscope to find yourself, and you would still have trouble. Now do it to everyone. Every human being alive on this planet, all 8 billion of us, every city, every crowd, every person you have ever met, and every person you never will, compressed the same way, would together form a cube about a centimeter on each side. A sugar cube. The entire human species. In a sugar cube sitting on your fingertip, and it would still weigh what we all weigh now, around 400 million tons. You could not pick it up. It would go straight through your finger, and the floor, and everything beneath. I am not telling you this to make you feel small. Quite the opposite, and I want to be clear about why. Nothing was removed in that thought experiment. Not one atom. Every person is still there, complete, all of them. The only thing taken away was the space between things. And that space is not a flaw. It is not wasted room. It is where chemistry happens. It is where molecules can form and fold and find each other. It is the reason a cell can exist, and a heartbeat, and a thought, and a person lying in a warm bed, listening to a voice at night. A neutron star has none of it. Nothing can happen there. It is perfectly, uniformly, silently full. You are the other thing entirely. You are almost entirely nothing, and that is precisely what makes you possible. Hold on to that, because we are about to start closing the gap. Which means the table your hand is resting on, the pillow under your head, the floor beneath the bed, all of it is more than 99.9% empty. What you feel as solid is not matter pressing against matter. It is the electric field around your atoms refusing to overlap with the electric field around theirs. Solidity is not a substance. It is a disagreement. Tonight we are going down to the one place in the universe where that disagreement is finally lost. I will tell you now what it is like there, so you have something to walk towards. On the surface of the object at the bottom of this staircase, if you held a small stone at waist height and simply let go, the whole fall would be over in about 1/1,000,000th of a second, and the stone would land with the energy of a small nuclear weapon. We will stand on that surface later tonight, when you are further along towards sleep. If you would like to come with me, a gentle like helps this quiet corner find the next person lying awake, and if you subscribe, the next journey will find you on its own. I would love to know where in the world you are listening from tonight. Now, between the water in your spoon and that surface, there are a lot of steps, and the first few are close to home. Pick up a fist-sized piece of granite, and you can feel it immediately, a certain seriousness in the hand that a piece of wood does not have. Granite is about 2.5 times the density of water. A cast iron pan is nearly 8 times. Lead is 11, and a lead weight the size of a sugar cube feels slightly wrong in the palm, as if someone has played a trick on you. And gold is 19. A cube of gold the size of a die weighs about as much as a small apple. That is why gold felt precious in the hand for thousands of years, before anyone knew what an atom was. It has presence. It sits in the palm with a weight out of all proportion to the room it takes up. There is one more thing on the kitchen scale worth mentioning before we leave the drawer, and it is the sea. Seawater sits at about 1.025 grams per cubic centimeter, very slightly denser than the water from your tap because of the salt dissolved in it. That difference is tiny, 2.5%. And yet, that 2.5% is the reason the oceans have layers. Cold, salty water sinks. Warm, fresher water floats. And because of that, the whole ocean turns over in a slow global circuit that takes about 1,000 years to complete. Water that sinks in the North Atlantic tonight will surface in the Pacific sometime around the year 3000. A 2.5% difference in density, moving the entire ocean on a schedule measured in millennia. I mention it because it is a useful reminder before we start taking enormous steps. Density differences do not have to be dramatic to do dramatic things. 2.5% runs the climate of a planet. We are about to deal in factors of 100 and 1,000 and eventually 1,000,000,000,000. But the ocean is a good place to start because it shows that the smallest differences on our staircase are already shaping the world you live in. Fill our teaspoon with gold and you are holding 95 grams. Roughly a small chocolate bar. You would not want to drop it on your foot, but you could still lift it with 2 fingers. And here is the thing worth noticing. The difference between cork and gold is not really a difference in how much stuff is there. It is a difference in how the emptiness is arranged. Same rules. Different architecture. And that raises the question that will carry us all the way down the staircase tonight. If ordinary matter is mostly empty space, what happens when something squeezes the emptiness out? Not partially. Not cleverly. Completely. That is not a question you can answer in a laboratory. No press on Earth is strong enough, and no material could contain the experiment even if it were. To find the answer, you have to go looking for a place where gravity has already run the experiment for you, patiently, over millions of years, using an entire star as the machine. But before we get anywhere near that, there is a step much closer to home. Because the densest natural material you can actually hold in your hand is not gold. Gold is not even close. There is a metal you have almost certainly never held and probably never seen that is denser than anything else you can pick up on this planet. Its name is osmium. It is a hard, brittle, faintly blue-gray metal. It looks a little like polished pewter with a cold cast to it, as though it has just come in from outside. It sits at 22.59 grams per cubic centimeter, comfortably heavier than gold, heavier than platinum, heavier than uranium, heavier than every other stable element that exists. Fill our teaspoon with osmium, and you are holding about 113 grams. Roughly a small pear. And here is where the strangeness starts, because a small pear is not heavy. You could carry one home without noticing. But when that weight arrives in a volume the size of a teaspoon, your hand receives it as wrong. Your arm has spent your entire life building a quiet expectation. Object this small, weight about this much. Osmium breaks that expectation, and the mismatch is what your body registers as surprise. This is worth pausing on, because it is the same trick that the rest of tonight's staircase will play on you, over and over, at ever larger scales. Density does not feel like weight. It feels like contradiction. Osmium is genuinely rare. All of it, ever refined by human beings, from every mine on Earth, over the whole history of the industry, would fit comfortably in a modest bathtub. It comes up mostly as a byproduct of platinum mining in a handful of places. It is also faintly unpleasant to be around, which is part of why you never see it. In powder form, it reacts with ordinary air to make a compound with a sharp smell that is genuinely dangerous to breathe. The name comes from the Greek word for smell, because the chemist who isolated it in 1803 noticed the odor before he understood what he had. But the reason it sits at the top of Earth's density list is what matters tonight. It is not simply that osmium atoms are heavy, although they are. It is that they pack efficiently. The atoms settle into a hexagonal arrangement, the same geometry a honeycomb uses, the same way oranges stack themselves at the bottom of a crate, and in that arrangement, there is very little wasted room between neighbors. On top of that, the electrons in osmium are held unusually tightly, drawn in close by the enormous positive charge of the nucleus. The atom is compact for its mass. Heavy center, small footprint, tidy stacking. Before we leave the kitchen, there is one more object I want to put in front of you, because it is the last step you could ever meet in ordinary life, and it already breaks the hand. Imagine 2 shoeboxes on the table. Identical size, one filled with water, one filled with osmium, the densest metal that exists on Earth. The water box weighs about 7 kilograms. Heavy, but you would carry it across a room without complaint. The osmium box weighs about 160 kilograms. That is more than 2 grown adults in a shoebox. You could not lift it. You could not slide it. 4 strong people with proper handles would struggle to get it off the table, and it would leave a dent in the table on the way. Same box. Same volume. One you carry with one hand. One you cannot move. And here is the part I would like to leave with you before we take the next step down. That impossible box, the one 4 people cannot shift, is the first landing on tonight's staircase. Osmium is where the entire Earth gives up. It is the heaviest thing this planet has to offer, and everything after it is a place where osmium would be considered light. By the time we reach the bottom, that same shoebox would outweigh every mountain range on the planet combined. We have a long way down. That is Earth's best effort. That is the maximum. 22.59. And I want to be honest with you about how modest that is, because we are only 2 steps down, and the staircase runs a very long way. A solid cube of osmium, 1 meter on each side, would weigh about 22.5 tons, around 15 family cars, in something the size of a washing machine. Placed in the middle of a room, it would go through the boards, through the joists, and keep going until it found something that could argue back. And yet on the staircase, we are walking tonight. Osmium is the first landing. Barely a beginning. Here is the reason. Everything about osmium's density comes from arranging atoms well. Better geometry, tighter electron shells, heavier nuclei. But the atoms themselves are still intact. Each osmium atom still keeps its electrons at a respectful distance from its nucleus. The empty space is still there. It has been tidied, not removed. Nature can tidy atoms only so far. Once you have the heaviest stable nucleus you can get, packed in the tightest geometry available, you have finished. You have reached the ceiling of what chemistry can do, which means that from here on, every step down the staircase requires something chemistry cannot supply. Something that does not tidy the emptiness, but destroys it. Something with enough force to push electrons out of the orbits they have held since the universe was 3 minutes old. But to find a force like that, we do not have to leave the planet. Not yet. Because there is a place where matter is being squeezed harder than any human machine has ever squeezed anything, and it is directly beneath your feet, about 6,000 kilometers straight down. Under the room you are lying in, there is rock. Under the rock, more rock, warmer. Under that, a layer of slow-flowing stone that behaves like tar over the course of centuries. And beneath all of it, at the center of the planet, there is a ball of iron and nickel about the size of the moon. The pressure at the center of the Earth is about 3.5 million times the pressure of the air in your bedroom. There is a fair question hiding in all of this, and it is worth answering before we go on. How does anybody know what the center of the Earth is like? Nobody has been there. The deepest hole ever drilled reached 12 kilometers before the rock became too hot to drill, about 1/500th of the way down. We know because of earthquakes. Every large earthquake sends waves through the whole planet, and they come in two kinds. One travels through liquid. The other cannot. Seismometers everywhere record when each arrives, and by comparing thousands of arrival times over a century, you can work backwards and map what the waves pass through. That is how we found the liquid outer core. One kind of wave disappears into a great shadow on the far side of the planet, and the solid inner core inside it, the waves speed up again, crossing into it. Nobody dug. Nobody looked. We listened to the planet ringing after it was struck, and drew a map of a place no one will ever visit. Everything else tonight was learned the same way. Nobody has been to a neutron star either. Let that sit for a moment. The deepest point in the ocean, where the water column would crush a steel sphere, is about 1,000 atmospheres. The center of the Earth is 3,500 times worse than that. Under that pressure, iron behaves in ways it never would in a workshop. The inner core is solid, despite being hotter than the surface of the sun, around 5,400 degrees Celsius. It should be a liquid at that temperature. It is not, because the pressure is squeezing it so hard that the atoms cannot find the room to flow past one another. Heat wants to melt it. Pressure refuses to let it. Pressure wins. So, Lego surely, at 3.5 million atmospheres, we have taken a big step down the staircase. We have not. And this is the first genuine surprise of the night. The density at the center of the Earth is about 13 grams per cubic centimeter. 13. Osmium was 22.59. The center of the planet is less dense than a lump of metal you could carry in your coat pocket. 3.5 million atmospheres, and it loses to a spoonful of gray metal sitting quietly on a bench at room temperature? The answer is in what iron had to work with. Iron's nucleus is much lighter than osmium's, 56 units of atomic mass against 190. Even squeezed by an entire planet, iron cannot make up that deficit. Compression at 3.5 million atmospheres buys you perhaps 30% extra density over iron at the surface. Useful, but nowhere near enough to overtake a metal that started nearly 3 times heavier. And that tells us something important about the staircase, something worth carrying down with us. Pressure alone does not get you very far. Not while atoms are still atoms. There is one more thing the Earth's core is doing while we are down here, and it will matter later tonight. It is generating a magnetic field. Above the solid inner core is a liquid outer core of molten iron, 2,000 kilometers thick, stirred constantly by heat from below and by the turning of the planet. Moving molten iron in loops generates a magnetic field, and that field is what turns every compass on Earth, shapes the aurora, and holds the solar wind off our atmosphere. Mars had one. It lost it a very long time ago, and after that, the solar wind had a much easier time stripping the air away. The full story of what happened to Mars is more complicated than one sentence can carry, but having a field clearly helps. So a ball of molten iron 6,000 kilometers beneath you, turning slowly, is part of the reason you have something to breathe. I mention it because of the number. Earth's field measures about half a Gauss at the surface. That is the entire output of a planet-sized dynamo, and the small magnet holding a note to your fridge is far stronger than that, close up against its own surface. Hold on to that. Half a Gauss. We come back to it much later tonight, when we meet something that beats it by a factor of 1,000 million million. 3.5 million atmospheres, a pressure that would flatten any human structure instantly, that no laboratory on Earth can sustain in anything larger than a diamond-tipped cell. The width of a grain of rice buys you a 30% improvement. That is all. Because the electrons are still holding their ground. They are being pressed hard. They are complaining, but they have not surrendered. And as long as they hold, the atom keeps its shape, and the emptiness stays. So if planetary pressure is not enough, what would be? The answer is that you do not need more pressure of the same kind. You need pressure of a completely different order, the kind you only get when something with a very great deal of mass has nothing at all holding it up. And there is such an object about 8 light minutes from where you are lying. You have seen it almost every day of your life. You have squinted at it, sheltered from it, planned your afternoons around it. It is only that you have never seen its middle. The sun is not solid. It has no surface you could stand on, no crust, no shore. It is a ball of gas, hydrogen and helium, held together by nothing but its own weight. And that is exactly why its center is interesting. The sun holds 330,000 times the mass of the Earth, and all of it is pulling inward at once. There is no rock underneath to take the load. The only thing holding the structure open is the fusion at the very center, converting 4 million tons of matter into pure energy every second. That balance, gravity pulling in, fusion pushing out, is what a star is. Not an object so much as an argument, held at a draw for billions of years. At the middle of that argument, the pressure reaches about 250 billion times the pressure of the air around you. We have just jumped from 3.5 million to 250 billion. That is a leap of 70,000. And the temperature there is about 15 million degrees. So how dense is the center of the sun? About 150 grams per cubic centimeter. Fill our teaspoon, and you would be holding about 750 grams. 3/4 of a kilogram. A large bag of sugar in the bowl of a teaspoon. We have finally overtaken osmium. 6.5 times over. The staircase is moving. But here is the thing that always stops me about the center of the sun, and it is worth slowing down for. It is a gas. Not a liquid. Not a solid. At 150 grams per cubic centimeter, 13 times denser than lead, the material at the heart of the sun still behaves as a gas. It flows. It swirls. It transmits sound. It obeys, more or less, the same equations that describe the air moving gently around your room right now. How can something 13 times denser than lead be a gas? Because it is not made of atoms anymore. Not really. At 15 million degrees, the electrons have been shaken loose from their nuclei by sheer heat. What is left is a plasma, a crowd of bare nuclei and free electrons, all moving at enormous speed, all mixed together, and a crowd of free particles is a gas, no matter how tightly you pack it. There is one detail about the sun's core that I think is the strangest fact in ordinary astronomy, and it belongs here. Light does not escape from the center of the sun quickly. You might reasonably assume that a photon born in the core simply flies out at the speed of light, crossing the 700,000 kilometers to the surface in a little over 2 seconds. That is what it would do in empty space. But the interior of the sun is not empty. It is a dense fog of free electrons and bare nuclei, and a photon traveling through it does not get far before hitting something. It is absorbed and then re-emitted a moment later in a completely random direction. Then it happens again. And again. The photon does not travel outward. It staggers. It takes a step, gets knocked sideways, takes another step, gets knocked back towards the center, and slowly, over an enormous number of collisions, works its way out purely by accident. The estimates vary, but the journey takes somewhere between 10,000 and 170,000 years. So the sunlight falling on your window this morning began its life in the core of the sun sometime in the last ice age. It was made when there were mammoths. It spent the entire history of human civilization bouncing between electrons, working its way outward a fraction of a millimeter at a time, and then covered the last 150 million kilometers to your face in 8 minutes and 20 seconds. The neutrinos we mentioned earlier do not have this problem. They are made in the same place, in the same reactions, and they leave immediately, straight out, at almost the speed of light, without touching anything. They arrive at Earth about 8 minutes after they are made. Same birthplace. Same instant. One takes 8 minutes. The other takes 100,000 years. That is what density does. That is the difference between something that interacts with matter and something that does not. In a place where matter is packed 150 times tighter than lead. This is the first place on our staircase where the atom breaks. Not from crushing, from heat. The electrons have not been pushed into the nuclei. They have simply been knocked out of their orbits and set loose to roam. And notice what that gives us. The empty space inside atoms, the vast 99.9% that made quark and gold possible, has partly closed. The nuclei can sit closer now because the electrons are no longer holding them apart in neat shells. That is where the extra density came from. Not from pressing atoms tighter, from dismantling them. But the sun's center is only a waypoint. It is dense because the sun is squeezing. Take the squeeze away, and it would puff back out at once. It has no strength of its own. It is dense the way a crowd is dense, because of the pressure at the doors, not because of anything about the people. The next step down is different. The next step is dense permanently, whether anything is pressing on it or not. But before we reach it, there is a detour I want to take you on. Because just as we are getting used to the idea that big things are dense, the universe offers us a star so enormous that you could drop the entire orbit of Jupiter inside it, Fendir, and it is emptier than anything you have ever touched. Step outside on a winter evening in the northern hemisphere and look for Orion. Find the 3 stars of his belt, then look up and to the left, to the shoulder. There is a star there with a distinctly warm color. Not white, not blue, Tuv, a soft orange-red, like an ember that has been left in the grate. That is Betelgeuse. It is about 700 light-years away, so the light landing in your eye tonight left that star around the time the great cathedrals of Europe were being built. Betelgeuse is enormous. Genuinely, absurdly enormous. If you removed our sun and put Betelgeuse in its place, the surface of the star would swallow Mercury, Venus, Earth, and Mars without pausing. It would very likely reach past the asteroid belt and out towards the orbit of Jupiter. Everything you have ever known, every ocean, every mountain range, every person who has ever lived, would be somewhere inside that star, far below its surface, with hundreds of millions of kilometers of glowing material overhead. It has about 700 times the diameter of the Sun. In volume, that is something like 300 million suns. And now, the number that matters for our staircase. The average density of Betelgeuse is somewhere around 1/10,000,000th of a gram per cubic centimeter. Take our teaspoon. Fill it with material from Betelgeuse. You would be holding roughly 1/2,000,000th of a gram. You could not feel it. You could not weigh it on any kitchen scale ever made. You would have to look very carefully to be sure the spoon was not simply empty. The star is less dense than the air in your room by a factor of about 10,000. In fact, the outer layers of Betelgeuse are a better vacuum than most laboratory vacuum chambers on Earth. If you could somehow stand inside the outer half of that star, protected from the heat, you would not experience it as being inside anything at all. There would be a faint, warm glow in every direction and essentially nothing to touch. That fact belongs on a staircase about density for one reason. It breaks the assumption that has been quietly forming in your mind that we are climbing steadily downward, and that bigger means denser. Betelgeuse says no. Betelgeuse is one of the largest objects you can see with your naked eye from your own garden, and it is made of almost nothing. It is enormous and empty. The two have nothing to do with one another. Why is it so thin? Because Betelgeuse is old and it is dying, and dying stars swell. As the hydrogen at the core runs low, the balance that held the star together starts to shift. The core contracts and heats. The extra heat pushes the outer layers outward. The star inflates like a slow, patient balloon, spreading the same amount of material across a volume hundreds of millions of times greater, same mass. Vastly more room. Density collapses. There is a recent event in the life of Betelgeuse worth telling you about, because it happened while most people listening were alive to see it, and for a few months, it looked as though we might be about to watch the collapse. In late 2019, Betelgeuse started to fade. That was noticed almost immediately, because it is one of the most watched stars in the sky. By February 2020, it had dropped to about a third of its normal brightness and fallen out of the list of the 20 brightest stars, and for a few weeks, there was serious public speculation that it was about to explode. It was not. By April, it had returned to normal. Betelgeuse had simply thrown off a large bubble of gas, which cooled into dust and sat in front of it like a veil. Betelgeuse coughed, and half the planet noticed. What that says is how loosely the star is held together. Our sun does not do this. The sun has flares and storms, but it does not casually throw off a chunk of itself large enough to be seen dimming from 700 light-years away. Betelgeuse can, because Betelgeuse is barely holding on. Its outer layers are so thin, and gravity's grip on them so weak at that distance from the center, that the star is genuinely shedding itself into space. It loses roughly 1 Earth mass of material every year. That is what the end of a star looks like from the outside. Not a countdown. Just a slow, undignified loosening, a giant losing its grip on its own edges, decades before the center finally gives way. So Betelgeuse is not a star that failed to become dense. It is a star in the process of collapsing into something far denser, a neutron star, or, if enough mass is still there at the end, a black hole. It has simply chosen to do the two things in the wrong order, to spread out first, dramatically, before falling in. Because Betelgeuse is going to collapse. Not tonight, and probably not in your lifetime, though the honest answer is that nobody can tell you when. It might be 100,000 years away. It might have already happened, and the light simply has not reached us yet. When it does, Betelgeuse will become bright enough to see in daylight, and it will stay that way for months. And at the center of that event, in about a quarter of a second, everything we have discussed so far will stop being relevant, because the collapse of a star does not tidy atoms, and it does not merely heat them. It removes the emptiness completely, all of it, permanently, and what is left behind is the object we came here for. But that quarter of a second is still several steps below us. Before we get there, we need to meet the last stop where matter still resembles anything you might recognize. A star the size of a planet, made of a substance that does not exist on Earth, holding itself up with a force that has nothing to do with heat. It is sitting 8.5 light years away, hiding in the glare of the brightest star in the night sky. Sirius is the brightest star in the night sky. If you have ever looked south on a clear winter evening and seen a star that seemed to flicker through several colors at once, that was almost certainly Sirius. It is close, only 8.5 light years away, and it is genuinely luminous, and the combination makes it hard to miss. But Sirius is not one star. It is two. For most of recorded history, nobody knew this. Then, in 1844, Friedrich Bessel noticed that Sirius was not moving across the sky in a straight line. It was wobbling, very slightly, over a cycle of about 50 years. Something was tugging on it, and from the size of the wobble, he could work out its mass. It came back as roughly the mass of our sun. An entire sun's worth of material, sitting beside the brightest star in the sky, completely invisible. It took 18 more years to see it. In 1862, a telescope maker named Alvin Graham Clark pointed the largest lens in the world at Sirius, and there, buried in the glare, was a point of light 10,000 times fainter than its companion, Sirius B. And when astronomers worked out what it was, the answer did not make sense for decades. Sirius B has about the mass of the Sun, but it is roughly the size of the Earth. Read that again slowly, because it is the largest single step on our entire staircase, and it is easy to skate past. An entire sun, squeezed into a ball the width of our planet. The Sun is 109 times the diameter of the Earth. That means Sirius B has taken the Sun's material and compressed it into about 1/1,000,000th of the volume. The density is around 1,000,000 grams per cubic centimeter. Fill our teaspoon with Sirius B, and you would be holding about 5 tons. A loaded delivery lorry in the bowl of a teaspoon. You could not hold it, of course. It would go straight through your hand, through the floor, through the foundations, and keep going. But the number is the point. We started this staircase at 5 grams in that spoon. We are now at 5 million grams. In 6 steps. This kind of object is called a white dwarf, and when they were first understood, nobody could explain them. Under the physics of the time, an object that dense with no fusion left to hold it open should simply have kept collapsing. It did not. And the reason it did not was one of the strangest discoveries in the history of physics. The thing holding Sirius B up is not heat, and it is not pressure in the ordinary sense. It is a rule. The rule says that no two electrons can occupy the same state at the same time. They are not allowed to. It is not that they repel each other, though they do. It is something deeper and stranger. Two identical electrons simply cannot be in the same configuration, in the same place, at once. The universe forbids it. Imagine a theater where every seat is numbered, and the rule is absolute. One person per seat, no exceptions, no sharing, no standing in the aisles. Now imagine a crowd being pushed in through the doors. At first, there is plenty of room. Then the front rows fill. Then the back. And eventually, there is nowhere left to sit, and the crowd at the doors, however hard it pushes, cannot get anyone else in. The room pushes back, not because the people are strong, but because the rule is. That is what is holding Sirius B up. Not strength. A prohibition. Physicists call the resulting force electron degeneracy pressure, and it has a wonderful property. It does not care about temperature at all. Sirius B could cool to absolute zero, and it would not shrink by a single meter. The support has nothing to do with heat. It is structural, permanent, and it will hold for as long as the star exists. There is a question that seems obvious once you have heard the numbers, and the answer is not what most people expect. Why can we not just go and get some? Not a whole star, obviously, but a sample. A few grams. Something to put in a laboratory and study. You might assume the problem is weight, that a spoonful would be too heavy to lift, too heavy to move, too heavy to contain, and that is true. But it is not the actual problem. The actual problem is that it would explode. Degenerate matter only exists while something is crushing it. Take a piece of white dwarf material, or neutron star material, and lift it away from the gravity that made it, and there is nothing holding it in that state anymore. The electrons that were forced into impossible proximity are suddenly free to spread out again. And they do. Instantly. Violently. A teaspoon of neutron star material, removed from its star and set down on a table, would not sit there being heavy. It would decompress explosively and violently, though exactly how violently depends on what you took and how deep you took it from, and nobody has ever been in a position to find out. Not because it is dangerous by nature, because it has been held under compression for millions of years, and the moment you release it, all of that stored pressure comes out at once. This is why there will never be a museum with a piece of neutron star behind glass. Not because we cannot reach one, because the substance cannot exist outside the conditions that make it. And so every fact we know about this material, the density, the strength, the behavior, has been worked out about a substance that has never been in a room with a human being, and never will be. We know the properties of something that would cease to exist the instant it arrived. There is an ending to the story of Sirius B that I find unexpectedly moving, and it is about patience. Sirius B is doing nothing. It has no fuel. Fusion stopped a very long time ago. It is simply sitting at about 25,000 degrees, radiating away the heat it was born with, and it will keep doing that essentially forever. A white dwarf cools the way a cast iron pan cools off the heat, slowly at first, then more slowly still, because the cooler it gets, the less it can shed. The curve never quite reaches zero. To go genuinely dark would take something in the region of a quadrillion years, about 70,000 times longer than the entire history of everything. Which means there are no black dwarfs. Not one. Not anywhere. Every white dwarf ever formed is still glowing. The universe has not existed long enough for a single one to finish cooling. Sirius B will still be warm when the sun has swollen, swallowed the Earth, and shrunk into a white dwarf of its own. An object the size of the Earth, holding the mass of the sun, quietly giving off heat for longer than the universe has been alive. So here, finally, we have arrived at something dense, in a way the sun's core was not. The sun's core is dense because something is squeezing it. Sirius B is dense by itself. Stop squeezing and it stays exactly where it is. And now you can feel the shape of the question that has to come next. If a rule is holding the star up and the rule has a limit, what happens when you exceed it? That question was answered by a 19-year-old on a boat in 1930. In the summer of 1930, a young man named Subramanian Chandrasekhar boarded a ship in Bombay, bound for England. He was 19 years old and had just won a scholarship to Cambridge. The voyage took about 18 days. He spent them doing arithmetic. The question he was working on was simple to state. Electron degeneracy pressure holds up a white dwarf. But if you keep adding mass to a white dwarf, gravity gets stronger. Does the rule hold forever? Or is there a point where gravity simply wins? He worked it through, combining the new quantum mechanics with Einstein's relativity, and by the time the ship docked, he had an answer. The rule breaks at about 1.4 times the mass of the sun. Below that line, electron degeneracy pressure holds. The star sits there, stable, potentially for longer than the current age of the universe, cooling slowly, and doing nothing dramatic at all. Above it, nothing holds. The collapse continues. That number, 1.4, is called the Chandrasekhar limit, and it is one of the most consequential numbers in astrophysics. It is a boundary line drawn across the sky, dividing every dying star into two fates. The reason the rule fails is elegant and worth a moment, because it is not obvious. Electron degeneracy pressure works because electrons refuse to share a state, and to avoid sharing, they have to move faster and faster as they get more crowded. Push them together, and their speed goes up. That speed is what generates the outward push. But there is a ceiling on speed. Nothing goes faster than light. So, as the star gets heavier and the electrons get pushed closer, their speeds climb towards the speed of light, and then they cannot climb any further. The pressure stops increasing at the rate gravity needs it to. Gravity keeps growing. Pressure hits its ceiling. And at 1.4 solar masses, the two lines cross. After that, there is nothing left to argue with. Chandrasekhar published the result, and it was not well received. Arthur Eddington, the most eminent astrophysicist alive at the time, and a man Chandrasekhar had genuinely admired, stood up at a meeting of the Royal Astronomical Society in 1935 and dismissed it publicly. He said, "There ought to be a law of nature to prevent a star from behaving in this absurd way." I want to say a little more about that argument, because it is one of the more human episodes in the history of science. Chandrasekhar was 24 when he presented the work in London. Eddington was 62 and arguably the most influential astrophysicist alive, and, importantly, Chandrasekhar's own colleague at Cambridge. He had seen the results in advance. He spoke immediately after the presentation, without warning, and dismissed the entire thing. Not with a counter-calculation, but with an appeal to common sense. The room agreed with him. Of course it did. Several senior physicists told Chandrasekhar privately that he was right. None of them said so publicly. It was not their field, and Eddington was Eddington. So he stopped. He wrote up everything he knew in a book and moved to a completely different subject. Then another. Over the rest of his career, he changed fields roughly every decade, mastering each one, writing the definitive book, and moving on. The limit was accepted within about 20 years. The Nobel Prize came 53 years after the boat. And here is the detail I find genuinely affecting. He and Eddington remained friendly. They went cycling together. Asked about that meeting in old age, Chandrasekhar said Eddington had been wrong, but not malicious. He simply could not accept a universe that permitted such an object. Nature permits it. That is the whole of tonight's episode. There is not. Chandrasekhar was right, and he received the Nobel Prize for it in 1983, 53 years after he did the work on the boat. So, above 1.4 solar masses, the electrons lose. What happens next? The electrons do not simply move aside. There is nowhere to move aside to. Instead, something far stranger happens. Under enough pressure, an electron is pushed directly into a proton. And when an electron and a proton are forced together, they do not stay two things. They merge. The electron's negative charge cancels the proton's positive charge, and what comes out the other side is a neutron plus a tiny, almost weightless particle called a neutrino, which departs immediately at very nearly the speed of light and is never seen again. This process has a name: electron capture. And when it starts happening throughout the core of a star, all at once, the consequences are extraordinary. Every electron that vanishes into a proton is an electron that is no longer holding anything up. The support does not weaken gradually. It evaporates. The pressure that was resisting gravity disappears in the same instant that the material becomes even denser and even easier to compress. The core does not settle. It does not sag. It falls. And it falls faster than almost anything else in the universe. I want to slow down here, because what happens next takes less time than a blink, and it is the single most important quarter second in tonight's story. Picture the core of a massive star just before the end. It is a ball of iron about the size of the Earth, sitting at the center of a star hundreds of times larger. It is holding itself up on electron degeneracy pressure, and it has just crossed the line. The electrons begin disappearing into the protons. The core starts to fall inward, and it accelerates, because every meter it falls makes gravity stronger and the support weaker. Within milliseconds, the inner part of the core is collapsing at around 70,000 kilometers per second. That is roughly a quarter of the speed of light. Inward. All at once. A region the size of the Earth becomes a region the size of a city. From about 5,000 kilometers across down to about 20, in something like a quarter of a second. To give that a shape you can hold, it is as though the entire Earth, every ocean, every continent, the whole planet, collapsed to the width of Greater London in less time than it takes you to say the word London. And it did not do it gently. Every part of it arrived at nearly a quarter of the speed of light. And then, abruptly, it stops. It stops because the same rule that held up Sirius B reappears, but this time it applies to neutrons instead of electrons. Neutrons also refuse to share a state. And neutrons are about 2,000 times heavier than electrons, which means they can be packed vastly tighter before that refusal kicks in, but when it does kick in, it is immensely stronger. The infalling core slams into this new wall, and, remarkably, it bounces. The rebound sends a shock wave, tearing back outward through the layers of the star that are still falling inward. Those outer layers have no idea anything has happened. They are still collapsing towards a core that no longer exists in the form they expect. The shock wave meets them head-on. What follows is a supernova. For a few weeks, that single star outshines the entire galaxy it lives in, 100 billion other stars, altogether outdone by one. But here is the part that most people do not know, and it is the detail that makes this chapter worth telling. 99% of the energy of that explosion does not come out as light. It comes out as neutrinos. Those tiny, almost weightless particles created during electron capture, they pour out of the collapsing core in unimaginable numbers. Everything else, the shock wave, the flying debris, and the light bright enough to outshine a galaxy, has to share what little is left. The visible light alone is a tiny sliver of that remainder. And we know this is true because we have measured it. On the 23rd of February, 1987, a star exploded in the Large Magellanic Cloud, a small companion galaxy to our own, about 168,000 light-years away. It became the closest supernova observed since the invention of the telescope. It is called SN 1987A. Roughly 3 hours before anyone saw the light, 3 separate detectors on Earth, one under a mountain in Japan, one in a salt mine in Ohio, one in the Caucasus, each registered a brief burst of neutrinos. 25 particles in total, across all 3, over about 13 seconds. 25 particles. That is all we caught. The star itself let go of something like 10 to the 58 neutrinos, a 1 followed by 58 zeros. By the time that flood had spread across 168,000 light-years and reached us, about 10,000 million of them crossed every square centimeter of this planet in those 13 seconds. Roughly 70 million passed through each human body, through the mountains, through the oceans, through the buildings, through every person who happened to be awake that night, and every person who was asleep. Nobody felt a thing. Neutrinos barely interact with matter at all. They pass through the entire planet as though it were not there, because to a neutrino, it very nearly is not. There is a human detail to SN 1987A worth adding, because someone had to be the first to see it. The star that exploded had a name before it died, Sanduleak-69 202, a blue supergiant about 20 times the mass of the Sun. It had been photographed many times. Nobody had paid it much attention. That night, an astronomer called Ian Shelton was at an observatory in Chile, photographing the large Magellanic Cloud. Routine work. He developed the plate and saw a bright star that had no business being there. His first thought was that the plate was flawed. So he walked outside in the middle of the night and looked up with his own eyes. It was there, bright enough to see without any instrument at all, in a galaxy 168,000 light-years away. He is, as far as anyone can tell, the first human being in nearly 400 years to see a supernova this close with the naked eye. The last was seen by Johannes Kepler. The universe had sent the message twice. First, the neutrinos, logged by machines in a mine, a mountain, and a tunnel with no human present. Then, 3 hours later, the light. We received it both times, and did not realize until afterwards that we had. I find something oddly comforting in this. On an ordinary evening in February 1987, a star died in another galaxy, and for 13 seconds, the news of it flooded through every living body on Earth, soundless, harmless, and completely unnoticed. Those neutrinos were the birth announcement. They were made in the exact instant that electrons and protons merged, in the exact instant that the core became something new. So on the 23rd of February 1987, we did not just watch a star explode. We watched a neutron star being born, and we caught the message it sent as it happened. But a newborn neutron star is buried inside an expanding wall of debris, and it takes a long time for that debris to thin out. To see one clearly, we need an older birth. One with a good written record. Fortunately, there is one, and the record was kept by astronomers who had no idea what they were looking at. On the 4th of July, in the year 1054, court astronomers in China recorded the appearance of a new star. They called it a guest star, the standard term for something that arrives in the sky unannounced. Their notes describe it as appearing near the star we now call Zeta Tauri in the constellation of Taurus. It was, they wrote, bright enough to be seen in broad daylight. It stayed visible in daylight for 23 days. For nearly 2 years, 653 days, by the Chinese record, it remained visible at night before finally fading from view. Independent records of the same event survive from Japan and from the Islamic world. There is a possible rock painting in Chaco Canyon, in what is now New Mexico, showing a bright star beside a crescent moon, in an arrangement that matches the sky on the morning it appeared. Nobody in 1054 knew what they were seeing. They recorded it faithfully anyway, and that turned out to matter enormously, because it means we know the exact birthday of one particular object in the sky. Point a modest telescope at that spot today, and you will find a faint, tangled smudge of light. It is catalogued as Messier 1, the very first entry in Charles Messier's famous list, added in 1758, largely because he kept mistaking it for a comet and wanted to stop wasting his own time. It is more commonly known as the Crab Nebula. The record of 1054 is better than most people realize. The primary Chinese record gives the date precisely, and Japanese and Islamic records confirm it independently. What is strange, and still unexplained, is the near total silence from Europe about an event that was visible in daylight for over 3 weeks. The Chinese court wrote it down because their job was to record anything unusual in the sky, on the reasoning that the heavens reflected the fortunes of the empire. They were wrong about why it mattered. But because they wrote it down anyway, we know the age of the crab pulsar to within a day, and that is one of the most useful measurements in modern astrophysics. The nebula is the debris. It is the outer layers of that star, still flying outward 970 years later, at about 1,500 kilometers per second. It is now roughly 11 light-years across, and it is still expanding, measurably, from year to year, in photographs taken decades apart. But the nebula is not the interesting part. At the exact center of that tangle, there is a point that flashes. It flashes 30 times per second. It is a neutron star. It is about 20 kilometers across, and it is turning on its axis 30 times every second, sweeping a beam of radiation past the Earth like a lighthouse. It has been doing this without interruption since 1054. Think about what that means for a moment. 30 rotations per second. Since 1054, that object has turned on its axis roughly 920 billion times since the Chinese court wrote down that a guest had arrived. It has not stopped, it has not stumbled, and, with the exception of a handful of tiny recorded glitches, it has kept a rhythm steady enough that astronomers use it as a clock, though it does drift, and it does occasionally stumble. The crab pulsar is also slowing down, very gradually. Every day, it takes about 40 billionths of a second longer to turn than it did the day before. That sounds like nothing. Over 970 years, it adds up. The object was spinning noticeably faster when the Chinese saw it. There are 2 details about that pulsar that I think are the most quietly astonishing in this entire episode, and neither of them is about size or weight. The first is what it looks like. The crab pulsar flashes 30 times per second. Point a good telescope at it, and you might expect to see it blinking, a rapid, obvious strobe. You do not. It looks like a perfectly ordinary, steady point of light. The reason is that the eye is simply the wrong instrument for the job. Those pulses are far too faint and far too quick to pick apart by looking, so what reaches you is the average of them, a steady point of light. It took a machine to see the flicker. So the Crab pulsar sits there, flashing 30 times a second, and for 200 years, nobody saw it do so. Astronomers looked straight at it and found an ordinary star. It took an instrument that could count faster than an eye, and until one existed, the whole history of this subject simply waited. The second detail is about sound. 30 times per second is not just a rotation rate. It is a frequency. And 30 hertz is inside the range of human hearing, just barely. It is roughly the lowest note on a large church organ, the one you feel in your chest more than you hear in your ears. So if you could somehow listen to the Crab pulsar directly, you would not hear a series of clicks. You would hear a single, continuous, very low note. A hum, held without pause since the year 1054. Radio astronomers do this routinely. They take the pulse data, shift it into audible range, and play it. The recordings exist, and they sound less like machinery than you would expect. The sky is full of held notes. We simply do not have the ears for it. And the energy it is losing as it slows has to go somewhere. It goes into the nebula. The entire Crab Nebula, all 11 light-years of it, grady, glows because it is being continuously energized by the small spinning object at its center, a city-sized star lighting up a cloud 11 light-years wide, purely by slowing down. Now, a newborn neutron star is a genuinely violent thing, a surface temperature in the millions of degrees, an enormous magnetic field, radiation pouring out in every direction. It has been cooling for nearly 1,000 years, and it is still glowing in X-rays. But it has not changed in the way that matters for our staircase. Its density has not shifted at all since the moment it formed. It will not shift in 1 billion years. The compression that happened in that quarter second is permanent. Which means we can finally do the thing we came here to do. We can fill the spoon. Take the teaspoon from the drawer. Hold it in your hand, the way you would if you were about to stir something. Feel how light it is. 5 grams of water if you filled it. A grape. Now fill it with the material at the core of a neutron star. It would weigh about 6 billion tons. I am going to give you that number several different ways, slowly, because it is the number this entire episode has been walking towards, and it does not land properly the first time. 6 billion tons. That is the combined weight of every car, lorry, bus, train, and aeroplane currently in service on the planet Earth, all of them, everywhere, at once, sitting in the bowl of a teaspoon. That is about 15 times the total mass of every human being alive. All 8 billion of us, 15 times over, in a spoon. That is roughly 1,000 Great Pyramids of Giza. The single most massive structure of the ancient world, built from 2.3 million blocks of limestone over 2 decades, 900 of them, in a spoon. That is a cube of solid steel, about 900 meters on each side. A steel block nearly a kilometer high, a kilometer wide, a kilometer deep, in a spoon. Let me put it in the room with you. If you could set that spoonful down on your bedside table, it would not sit there. It would pass through the table without slowing, through the floor, through the foundations, through the soil and the bedrock beneath, and it would keep going. It would not stop at the mantle. It would fall all the way to the center of the earth, and then, carrying all that momentum, it would rise most of the way up the other side, slow, stop, and fall back. It would oscillate through the planet, back and forth, for a very long time. And it would do that not because it is large. It is the size of a spoonful. It would do that because there is simply nothing on earth solid enough to hold it. Now I can's the honest detail, because I would rather you have the accurate picture than the dramatic one. The average density of a neutron star is somewhere around 400 million tons per cubic centimeter. At that density, a teaspoon comes out closer to 2 billion tons. 6 billion is the figure for the core, the deepest region, where the density roughly doubles or triples again. Both numbers are real. They just describe different depths. When you hear a teaspoon weighs 1 billion tons, and when you hear 6 billion, nobody is exaggerating. They are standing at different points inside the same star. So let us say it precisely. Taking the star as a whole, a teaspoon of it comes out at around 2 billion tons. Down in the core, around 6. Now look at the staircase we have walked down. We started at 5 grams. Water. A grape in a spoon. Osmium took us to 113 grams. A small pear. The center of the Earth, about 65 grams. Submarine canyons, less than the osmium, our one step backwards. The heart of the sun, 750 grams. A bag of sugar. Sirius B, a star the size of a planet, 5 tons. A loaded lorry. And now 2 billion tons, taking the star as a whole. 6 billion down in the core. From a grape to 2 billion tons in the same spoon. That is a factor of 400 trillion from the top of the staircase to the bottom. And here is what I would like you to sit with as the room goes quiet around you. All of that difference comes from one thing. Not from exotic material, not from strange atoms, not from anything you could call a substance you have never met. It comes from removing the empty space. Everything in your bedroom is more than 99.9% nothing. The pillow, the walls, the air, your own hands. Every atom is a tiny nucleus with a vast, quiet emptiness around it, held open by electrons that will not be crowded. A neutron star is what is left when something closes that emptiness. All of it. Permanently, and the atoms themselves do not survive the process. There is no new ingredient. Nothing was brought in from outside. The universe took ordinary matter, the same protons and electrons that make up your bones and the water in your glass, and pressed, until the space between them was gone, and until most of those protons and electrons had merged into neutrons. So, it is not quite the same stuff. But it is not a substance from somewhere else either. 2 billion tons in a spoon is what our own kind of matter becomes when you take the emptiness out of it. That holds, at least, from the crust down through most of the star. What the matter is doing at the very center is a different question, and it is one nobody has answered yet. We will go down there later tonight, when you are closer to sleep. But knowing the density is only knowing one number. It tells you nothing about what such an object is actually like, what its surface looks like, what happens to a stone you drop on it, how fast it turns, how hard it is. And it is very hard. That is the part that surprised me most when I first went looking. Not the weight, the hardness. We are about to meet a mountain 5 millimeters tall that no force in the universe can flatten. There is a neutron star about 3,600 light-years away in the direction of the constellation Camelopardalis, catalogued as PSRJ 0740 plus 6620. It is the heaviest one we have ever weighed properly, about 2.08 times the mass of the Sun, and it is roughly 25 kilometers across. 25 kilometers is a distance you know. A comfortable morning cycle. In London, it takes you from Heathrow to Canary Wharf, the full width of the city. In New York, Manhattan end to end, twice over. Now put 2 suns in there. Not 2 sun-sized objects. 2 suns worth of material. Every atom of hydrogen and helium and carbon and iron that 2 stars contain, packed into the space between one side of a city and the other, and not loosely. There is no puffed-up envelope of light gas around it the way there is around the Sun. Above the solid surface, there is only a film of gas we will come to shortly, and it is barely a centimeter deep. From that surface downward, it is dense all the way, and it keeps getting denser. By the time you reach the center, the material is several times heavier again than the crust you landed on. Which leads to something I find genuinely lovely. You could walk across a neutron star in an afternoon. You could not, for 100 reasons we will get to. But in terms of pure distance, the surface of the densest star in the universe is a shorter walk than most people do on a weekend. Set off from the North Pole and you would reach the equator in about 4 hours. Betelgeuse, the largest object your eyes can pick out on a clear night, could swallow the orbit of Jupiter. The densest star in the universe would fit inside the ring road of a single city. Both of them started as the same kind of star. Now, how do we know the mass so precisely? This is my favorite piece of astronomy because it uses Einstein to weigh something nobody can see. PSRJ 0740 plus 6620 has a companion, a white dwarf, orbiting every 4.5 days, twice per orbit. That companion passes between us and the pulsar. And when it does, the pulsar's signal has to travel through the curved space around it. Curved space is longer than flat space. So the pulse arrives late, by about 30 millionths of a second. 30 millionths of a second, measured across 3,600 light years. And from that delay, from a pulse being very slightly tardy, astronomers calculate the mass of the thing that got in the way. That is the whole method. Something is late, and from its lateness, we learn its weight. There is a second method, and it agrees. An instrument called NICER, bolted to the outside of the International Space Station, watches the hot spots on a neutron star's surface as it rotates. Space around the star is curved so strongly that light from the far side bends towards us, so a hot spot does not vanish cleanly when it rotates out of view. It lingers. How much it lingers depends on the ratio of mass to radius. Two completely independent methods, using two different consequences of relativity applied to the same object. They agree. That is how you become confident about a thing you will never visit. There is a limit to how heavy a neutron star can get, and this one sits uncomfortably close to it. Somewhere above 2, perhaps 2.5 solar masses, even the refusal of neutrons to share a state gives out, and then there is nothing left. The collapse continues and does not stop, and what forms is a black hole, which makes a neutron star the last thing in the universe that is still an object. The final step where there is something there to describe. Below it, there is only a region of space with a rule about it. And on the surface of that last object, there are mountains. They are 5 millimeters tall. The closest neutron star we know of is called RxJ 1856.5 minus 3754, about 400 light-years away, in the constellation Corona Australis. It is quiet, not accreting anything, not flaring, simply drifting through space, cooling, minding its own business. Because it is close and calm, it is one of the very few whose surface we have measured. The surface of a neutron star is not a metaphor. It is a real, solid crust, about a kilometer thick. And if you could stand on it, it would be the smoothest surface in existence. The tallest mountain on it is about 5 millimeters high. 5 millimeters. A stack of about 50 sheets of paper. A grain of rice standing on its end. That is not a limit of our measurement. That is close to the most the crust is thought to be able to hold. Anything higher, gravity flattens immediately. Shrink the Earth to the size of a snooker ball, and Everest becomes a roughness you could just feel with a fingertip. Shrink a neutron star to the same size, and its highest mountain would be about the width of a single atom. It is smoother than anything human beings have ever manufactured, including the mirrors in gravitational wave detectors, the smoothest objects ever made by hand. But here is where it becomes properly extraordinary. That 5 millimeter mountain would weigh about 10 billion tons. A bump the height of a grain of rice, weighing more than every building in every city on Earth put together, and it cannot be flattened. Not by anything. The crust of a neutron star is the strongest material in the universe, and this is measurable. Simulations that model it atom by atom, The way engineers model steel put its breaking strength at roughly 10 billion times that of steel. Steel is what we build bridges out of. It holds up buildings, carries trains, forms the hulls of ships. Now multiply the load it fails at by 10 billion. Why so strong? Because of how it is arranged. At the top, atomic nuclei, mostly iron, packed into a rigid crystal lattice, 100,000 times more tightly than in any ordinary metal. Go deeper, and the pressure squeezes the nuclei until they can no longer stay round. They stretch. They flatten. They merge into shapes that exist nowhere else in nature. Long rods, flat sheets, tubes with holes through them. Physicists, who have a better sense of humor than they are given credit for, named these shapes after pasta. There is spaghetti, coppe, long rods. There is lasagna, too, flat sheets. There is bucatini, the tube with the hole. There is even a phase they call Swiss cheese, where the arrangement inverts and you get bubbles of empty space inside a solid mass. The names are a joke. The physics is completely serious. These are real predicted phases, and the shapes come from a genuine competition, the strong nuclear force pulling nuclei together, electric charge pushing them apart, reaching a truce at different geometries, depending on depth. And this is where the strength lives. Steel is strong because of chemical bonds between atoms. Here, there are no chemical bonds left at all. The crust is a crystal of bare nuclei, locked in place by their own electric repulsion at a density no chemistry could survive, and deeper down by the tug of war between that repulsion and the nuclear force. There is one more thing about that surface that sounds like a mistake the first time you hear it. A neutron star has an atmosphere. Not a metaphorical one. A real layer of gas above the solid surface, in exactly the sense that Earth has air above its rock. It is about 1 centimeter thick. The entire atmosphere of a star, from the surface to the edge of space, the thickness of a fingernail. Gravity presses the gas into a film. It is thought to be made of the lightest elements, hydrogen or helium, depending on the star, and it is the layer that produces the light our telescopes actually detect. Everything we know about a neutron star, we learned through 1 centimeter of air. Pick up a small stone. Hold it at waist height, about a meter off the ground, and let it go. On Earth, it falls for 4/10 of a second and lands at roughly 16 kilometers an hour. A soft knock. Now stand on a neutron star and do the same thing. The stone falls 1 meter. It arrives at approximately 7.2 million kilometers per hour. That is 2,000 kilometers per second. 0.6% of the speed of light from falling 1 meter. The whole fall takes about 1/millionth of a second. Far too fast to see, far too fast for a nerve signal to reach your brain. The stone would be gone before you knew you had let go. And the energy released when it landed would be comparable to a small nuclear weapon. From a pebble falling 1 meter. Surface gravity there is about 200 billion times Earth's. Here is a way to feel that without any numbers. Lift 1 foot off the floor, just a few centimeters. That is nothing. You could hold it there for a minute without thinking. On a neutron star, lifting that same foot the same few centimeters would take more energy than detonating 100 tons of high explosive to lift 1 foot. Once, you would not be crushed slowly. Every atom in your body would be pressed into a layer a few atoms thick, faster than a nerve impulse can travel from your ankle to your spine. There would be nothing to feel it with, and no time in which to feel it. Which is, in a strange way, the gentlest thing about the whole place. But there is a second effect of that gravity, and it is stranger than the crushing. Light does not travel straight there. Gravity bends the path of light so severely that photons leaving the far side of the star curve around the edges and come towards you anyway. Which means if you looked at a neutron star from a safe distance, you would not see half of it, the way you see half of a football. You would see about 3/4 of its entire surface at once. The far side, wrapped around the edges, stretched and smeared into a ring near the rim, as though you were looking through the bottom of a glass, and if you stood on it and looked straight up, you would see more sky than ought to be possible. The horizon pushed down and away from you, and stars that should be hidden below your feet bent up over the edge of the world into a bright, crowded band all around you. None of this is speculation. It is a direct consequence of general relativity, and the same mathematics is used routinely to interpret real X-ray observations. We simply have no way to photograph it. There is a third effect, quieter than the others. Time runs slowly there. A clock on that surface ticks about 1/4 slower than one far away in empty space. Spend an hour there, and roughly 1 hour and 20 minutes passes for everyone else. You would notice nothing. Your watch, your heartbeat, your thoughts all slow together. The universe outside would simply appear to be in a hurry. And all of this is on a star that is standing still. Most of them are not standing still. Deep in a globular cluster called Terzan 5, about 18,000 light-years away, there is a neutron star that rotates 716 times per second. Not per minute. Per second. Try this. Tap your finger on the bed as fast as you possibly can. Most people manage between 5 and 10 taps a second before the hand refuses. Now multiply your fastest by about 100. That object, 25 kilometers wide, heavier than the sun, completes a full rotation in 1.4 milliseconds. In the time it takes you to blink once, it has turned around more than 200 times. Its equator moves at about 56,000 kilometers per second, very nearly 1/5 of the speed of light. It is running close to the limit. Spin much faster than this, and a star begins shedding material off its own equator. The only thing keeping this one whole is that its gravity is still narrowly winning. Why so fast? 2 reasons, and they compound. The first you have felt with your own body, if you have ever sat on a swivel chair and pulled your arms in, you speed up. The star did exactly this when the core collapsed from 5,000 kilometers across down to 20. Whatever slow rotation it had was concentrated into a body 250 times smaller across. A star that turned once a month came out of the collapse, turning several times a second. But that alone does not get you to 700. The rest of it is that this one has been fed. It has a companion, and it has been pulling material off that companion for a very long time. That material spirals in, lands on the surface, and delivers a tiny push each time, like a hand on a roundabout, over and over, for millions of years. Now, the rotation matters tonight, but not for the speed itself. It matters because rotation is how we found these objects at all. In the summer of 1967, a PhD student named Jocelyn Bell was working with a new radio telescope in a field outside Cambridge. A strange instrument, 4.5 acres of wire and wooden posts, built largely by hand by the students themselves. The data came out on rolls of paper, drawn in ink by a moving pen. Bell was reading those rolls by eye. Nearly 30 meters of chart paper every day. And she noticed something she described as a bit of scruff, a small irregular smudge that kept appearing at the same point in the sky, coming back 4 minutes earlier each night, exactly as a fixed star would. She got the pen recorder to run faster, to spread the signal out and see its shape. It was a train of pulses, perfectly, impossibly regular. One every 1.33 seconds. Nothing in astronomy was that precise. The regularity was so unnatural that the team half-seriously labeled the source LGM1, Little Green Men, while they worked out whether they had detected another civilization. Then, Bell found a second one in a completely different part of the sky at a different rate. 2 independent civilizations, both broadcasting, both using metronomes. It had to be natural. It was a neutron star, the first ever detected. Still there, still turning, still catalogued as PSRB 1919 plus 21, and it has not missed a beat since. The paper announcing the discovery was published in 1968 with 5 authors. Bell's name was second. The Nobel Prize was awarded in 1974, and it went to 2 people. She was not one of them. She has spoken about this over the years with a graciousness I find genuinely moving. In 2018, she was awarded a special breakthrough prize worth about $3 million and gave the entire sum away to fund physics PhDs for students from underrepresented backgrounds. There is something fitting in that. The first neutron star was found by someone reading 30 meters of paper a day, by eye, looking for something nobody had told her to look for. There is a fridge magnet somewhere in your home. Its field is about 100 Gauss. The Earth's magnetic field, the one that turns a compass and shapes the aurora, is about half a Gauss, weaker than the fridge magnet, spread across an entire planet. A hospital MRI scanner is around 15,000 Gauss. Strong enough that a steel cylinder brought into the room becomes a genuine danger. An ordinary neutron star has a magnetic field of about 1,000,000,000,000 Gauss, and roughly 1 in 10 reaches 1,000 times higher still. A quadrillion Gauss. A 1 followed by 15 zeros. These are called magnetars, and the word means exactly what it sounds like, a neutron star with an exceptionally strong magnetic field. Same object, same density, same city-sized body. Only the magnetism is different, and it is different by a factor of 1,000. At a quadrillion Gauss, magnetism stops being a force acting on matter and becomes something that reshapes what matter is. Atoms cannot stay round. They are squeezed into thin needles, aligned with the field, perhaps 200 times longer than they are wide. Chemistry, which depends entirely on round electron clouds, simply stops working. And it does not stop at matter. At those field strengths, empty space itself starts to behave like a lens. Nothing is there. The nothing bends light. Now, let me tell you what happened on the 27th of December, 2004. A magnetar called SGR 1806-20, about 50,000 light-years away, on the far side of our own galaxy, with the entire galactic center between us and it, had a starquake. Its crust, that impossibly strong crust, cracked. The magnetic field lines threaded through it, snapped and reconnected. In 1/10 of 1 second, it released more energy than the sun produces in 150,000 years. That burst crossed 50,000 light-years. And when it arrived, it was still strong enough to overload the detectors on essentially every X-ray satellite in orbit, several of which had to be reset. It measurably ionized the Earth's upper atmosphere, oblaverse, from the night side of the planet. It bounced off the moon and was detected as a reflection. Briefly, it was the brightest object ever observed from outside our solar system. Here is the detail I want to leave you with. The Sun is 150 million kilometers away. SGR 1806-20 is about 3 billion times further. And for 1/10 of a second, that object, 3 billion times more distant, but ionized the upper atmosphere of this planet and overwhelmed detectors on satellites built to stare at the sky, from a body 25 kilometers across. From a crack in its crust, nobody noticed. There was no light in the sky, no sound, no interruption to anything. People went to work on the 28th of December, 2004, entirely unaware that the night before, the strongest magnetic object known to science had reached across half a galaxy and touched the air above their heads. There is a more recent event from 2020 that went a long way towards solving a mystery over a decade old. Since 2007, radio telescopes had been picking up something inexplicable, extremely brief, extremely bright bursts of radio waves, lasting a few thousandths of a second, arriving from all over the sky. In a millisecond, they released as much energy as the sun does in several days. And they came from other galaxies, billions of light years away. Almost nothing fits both requirements. To vary in a millisecond, an object cannot be more than a few hundred kilometers across. so something smaller than a large city, releasing days of sunlight in 1,000th of a second, in galaxies far too distant to examine. The theories became increasingly exotic. Some were quite serious about alien technology. Then, on the 28th of April, 2020, one went off inside our own galaxy. It came from SGR 1935 plus 2154, a magnetar about 30,000 light-years away. 2 radio telescopes recorded a fast radio burst from exactly that position at exactly the moment X-ray satellites recorded a burst from the same object. Same source, same instant. 2 completely different kinds of telescope. 13 years of one of astronomy's more baroque mysteries, and here at last was proof that a magnetar can make at least some of them. Whether every one of those bursts comes from an object like this is still an open question. Magnetars are short-lived by cosmic standards. The field decays over roughly 10,000 years, and then they settle into ordinary neutron stars. But while they last, they demonstrate what the rest of tonight's staircase has been building towards. Everything we have met, the hardness, the spin, the magnetism, the bent light, the slowed time, comes from one source. All of it is what happens when you take an ordinary star and remove the empty space. There is one region left, one place we have not been, and it is the only place in this entire story where the honest answer is, we do not know. On the 17th of August, 2017, 2 detectors, one in Louisiana, one in Washington State, to guess, recorded a signal that lasted about 100 seconds. It was a rising note. A slow chirp climbing in pitch, getting faster and faster before stopping abruptly. That sound, translated into something a human ear can hear, is 2 neutron stars spiraling into each other. And it is genuinely a sound in the sense that matters, a vibration arriving as a wave, converted to audio without changing anything about its structure. The universe played a note, and we heard it. The 2 stars had been circling each other for a very long time, most likely billions of years, closing the gap a little at a time. In the final 100 seconds, the orbit tightened catastrophically. They went from a few turns per second to a few hundred. Then they touched. The collision happened 130 million light-years away, in a galaxy called NGC 4993. 1.7 seconds after the gravitational waves stopped, 2 space telescopes detected a burst of gamma rays from the same patch of sky. That gap is one of the most valuable measurements in modern physics. Gravitational waves and light had raced each other across 130 million light-years and arrived within 2 seconds of one another, and gravity therefore travels at the speed of light, to within about 1 part in 1,000 million. The alert could only narrow the location to a patch of sky 30 times the size of the full moon. So the race began. Telescopes across South America, Africa, Australia, and Antarctica. Everywhere it was currently night, photographing galaxies one after another, looking for a point of light that had not been there before. The Swope telescope in Chile found it first, 11 hours after the collision. Over the next 2 weeks, roughly 70 observatories and 3,500 astronomers, close to a third of the entire profession, watched that single point brighten, turn from blue to deep red, and fade. That color change was the evidence. Blue at first, then reddening fast, because heavy elements are extremely good at absorbing blue light and terrible at letting it through. The glow reddened because it was being filtered through a freshly made cloud of heavy metal. And in that spectrum was the thing people had waited decades for, the signature of heavy elements being built, right there in the debris. Strontium was picked out and named. The rest of that family were forged in the same process, too tangled at that distance to tell one from another. Gold is one of them, and not a trace either. The models put the whole haul of heavy elements at thousands of times the mass of the Earth, the gold alone, somewhere between a few Earth masses and a few hundred, depending on whose model you take, made in seconds, thrown outward into the galaxy. Here is why that mattered. We had a good account of where most elements come from. Hydrogen and helium from the Big Bang. Carbon, oxygen, nitrogen, silicon, all the way to iron, submarine, forged inside stars, step by step by fusion. But fusion stops at iron. Past iron, fusing atoms costs energy rather than releasing it. So the heavy elements, gold, platinum, uranium, the rare earths in every phone and every wind turbine, lineal, had to come from somewhere else, and nobody could say with confidence where. Supernovae were the leading candidate, but the numbers never worked. They did not produce nearly enough. GW170817 was the first time anyone watched it happen. When two neutron stars collide, they fling out an enormous quantity of almost pure neutrons. Free neutrons are unstable on their own. They last about 15 minutes, so they immediately begin sticking to whatever nuclei are nearby. And because there are so many, nuclei absorb neutron after neutron faster than they can decay, building elements far heavier than iron in seconds. Gold takes shape in about 1 second. Which brings us back to your hand. If you are wearing a gold ring, or a chain, or if you have a gold crown on a tooth, touch it for a moment. Not one atom of it was made on Earth, and not one of them was made by ordinary fusion inside a star. They were forged in an event like this one, or in something else just as violent. Not in the sun, not on Earth. Made in seconds, somewhere in this galaxy, in something violent enough to build an atom that heavy, most likely 2 dead stars, each the size of a city, each denser than anything in your experience, finally falling into each other after billions of years of circling. That gold drifted through interstellar space for a very long time. Some of it ended up in the cloud that collapsed 4.5 billion years ago into the sun and the planets. Most sank towards the Earth's core and is still down there, unreachable. What we can actually mine arrived later, delivered by asteroid impacts after the crust had solidified, a late veneer sprinkled on top. So the ring on your finger has had an unreasonable journey, forged in a collision between two neutron stars, adrift for billions of years, folded into a forming planet, delivered to the surface by an asteroid, dug out of the ground, melted, shaped, sold, and given to someone. And now it is resting on a hand in a quiet room, at night, while someone drifts towards sleep. The same is true of the platinum in a catalytic converter, and the uranium in a reactor, and the neodymium in the tiny magnet inside your headphones, and, in trace amounts, the iodine your thyroid needs, which is sitting in your throat right now, doing its job. None of it can be made by ordinary fusion inside a star. We began with a teaspoon of water, and we have arrived, step by step, at an object where that same spoon holds 2 billion tons. But everything so far has been the outside. The crust is a kilometer thick. Beneath it, there are another 11 or 12 kilometers down to the center, and that is where things stop being knowable. Go down through the crust, and the nuclear pasta gives way. The nuclei finally dissolve completely. What is left is a fluid of free neutrons, with a small number of protons and electrons mixed in. And that fluid is a superfluid. A superfluid flows with no friction at all. On Earth, we can make helium do this, but only within a couple of degrees of absolute zero, en route. And even then, it climbs the walls of its own container and escapes over the rim. Inside a neutron star, the fluid is at hundreds of thousands of degrees, and superfluid anyway, not because it is cold, but because it is so dense the neutrons pair up and move as one thing, which means at the center of the hardest object in the universe, wrapped inside the strongest material that exists, there is an ocean that never stops moving, no friction to slow it. Nothing to stop it. It has been circulating since the star formed, and it will circulate until the star is gone. The protons in that mixture are stranger still. They are a superconductor, carrying current with no resistance at all. That is thought to be part of what holds the star's colossal magnetic field in place across millions of years. In an ordinary conductor, the current would fade away. Here it barely does. Go deeper still, past the halfway point, and we reach the place where physics runs out. At the center, the density is perhaps 5 to 10 times that of an atomic nucleus. And nobody knows what matter does there. It has never been made. It cannot be made. No accelerator on Earth reaches it. There are 3 main possibilities, and they are all strange. The first is that it is simply more neutrons, packed even tighter, still recognizably neutrons, holding on. The second is that at some depth, the neutrons stop being neutrons. A neutron is not fundamental. It is 3 smaller particles called quarks, held together by the strong nuclear force. Under normal conditions, quarks can never be separated. Pull 2 apart and the force between them grows until it snaps and makes new particles instead. But at extreme enough density, that confinement may fail. Not because the quarks are pulled apart, but because the neutrons are pushed so close together that there is no longer any meaningful boundary between one and the next. The quarks would find themselves in a continuous sea, free to move, no longer belonging to any parent particle. If that is happening, then at the center of a neutron star, there is a substance that has existed only once before in the history of the universe. In the first few millionths of a second after the Big Bang, when everything was hot and dense enough for quarks to roam free. A neutron star core would be a small pocket of the early universe, preserved by pressure, sitting quietly in the present day. The third possibility involves particles called hyperons, heavier cousins of the neutron that cannot exist for more than a fraction of a second under normal conditions. Under this much pressure, they might be stable. We do not know which is right. We may find out. Every neutron star merger we detect carries information about how squeezable these objects are, because in the final moments before collision, each star deforms the other, and how much it deforms depends on what is inside. That deformation is written into the gravitational wave signal. But for tonight, I would rather leave it as it is, because there is something quietly wonderful about the fact that the densest thing in the universe is also, in a very literal sense, the least understood. We can tell you its mass to 3 decimal places. We can tell you its radius, its spin, its magnetic field, its temperature. We can measure a pulse arriving 30 millionths of a second late across 3,000 light years. And we cannot tell you what it is made of in the middle. That is where the staircase ends. Not at an answer. At a question, sitting in the dark, about 12 kilometers beneath the smoothest surface in existence. I want to end the science with 2 small human things, because I think they say something the numbers cannot. The first is a joke. Arthur C. Clarke published a very short story called Neutron Tide. Barely 2 pages. A naval officer describes a spacecraft that strayed too close to a neutron star and was torn apart. A search party recovers the wreckage. Only one fragment survived, twisted beyond recognition by gravity. It was, the officer explains, a star-mangled spanner. That is the whole story. The entire piece exists to deliver that pun, and Clarke knew exactly what he was doing. He ends by apologizing to the reader, but I keep coming back to it, because for a joke like that to work, the audience has to already understand that a neutron star will destroy anything that comes near it. 3 years after the first one was found, that understanding was already common enough to build a punchline on. We met the most extreme thing in the universe, and within 3 years, we were making jokes about it. The second thing is not a joke at all. In the late 1970s, NASA launched 2 spacecraft towards the outer solar system. Voyager 1 is now about 25 billion kilometers away in interstellar space, the most distant human-made object in existence, and it will keep traveling essentially forever. Bolted to the side of each spacecraft is a gold-plated record. On it are greetings in 55 languages, the sound of rain, a heartbeat, whale song, a kiss, and 90 minutes of music. And on the cover of that record, etched into the metal, there is a diagram. A starburst. 14 lines radiating from a single point, each of different length, each with a pattern of binary marks along it. The point in the center is the sun. The 14 lines point to 14 pulsars. Each line's length gives the distance. Each binary pattern gives the exact period of that pulsar's rotation. Here is why it works as a map. Every pulsar has its own precise rate. No two are identical. And those rates change over time in a completely predictable way as the star slowly spins down. So anyone who finds that record anywhere at any time can identify each of those 14 pulsars by its rhythm, triangulate the position of the sun from 14 directions at once, and by measuring how much each has slowed since the periods etched on the cover, calculate when the record was made. A map in space and a timestamp using nothing but the rotation of dead stars. The map is drawn in binary, the simplest counting system any civilization would arrive at. But the unit of time is not the second. A second is a human invention, tied to the rotation of one particular planet, and would mean nothing to anyone else. Instead, the unit is the transition period of the hydrogen atom, about 700 picoseconds. Hydrogen is the most common element in existence, and that number is the same everywhere, in this galaxy and every other, at the beginning of the universe and at the end. Anyone, anywhere, studying hydrogen will find it. No language. No shared history. No assumptions, except that the finder knows what hydrogen is and can look at the sky. Now think about what that required us to believe. We had known neutron stars existed for 10 years. 10. And we were already confident enough in their reliability to use them as the permanent address of the human species, to bet that in 100,000 years, or 1,000,000, those 14 objects would still be turning at rates we could predict from the day it launched. That confidence was not misplaced. Every one of those 14 will still be spinning long after the sun has swollen, swallowed the inner planets, and shrunk into a white dwarf. They will still be spinning when the Earth is gone. So there is a golden record, moving through interstellar space, with the location of our home written on it in the language of collapsed stars. We use the densest objects in the universe to sign our name. And there is one more thing worth saying about how we came to know any of this. Nobody has visited a neutron star. Nobody ever will. Every number tonight was worked out from a distance, by people with no direct access to the thing they were describing. A wobble in the position of Sirius, noticed nearly 2 centuries ago, led to a star nobody could see. 18 days of arithmetic on a boat by a 19-year-old drew a line that divides every dying star into 2 fates. 30 meters of chart paper a day, read by eye in a field outside Cambridge, turned up a piece of scruff that was a collapsed sun. 25 particles, caught in a mine and a mountain and a tunnel, told us a star had died in another galaxy 3 hours before the light arrived. None of that required going anywhere. All of it required paying attention to something small for a long time without knowing in advance whether it would come to anything. That is the actual method. Not telescopes, not equations, those are tools. The method is noticing. We have come a long way down tonight, and I would like to spend a few minutes at the bottom before we climb back out. No new facts from here. Just a few thoughts, quietly, while the room stays dark. The first is about emptiness. Everything we found tonight came from a single idea, that ordinary matter is mostly nothing at all. Your hands, the pillow, the walls, the ground beneath the building. More than 99.9% empty. Solid things are not solid. They are arrangements of almost nothing, held apart by a rule. And a neutron star is what happens when that emptiness closes. Nothing was added. No exotic ingredient. The universe took the same protons and electrons that make up your bones and the water in your glass and pressed until the space between them was gone. 2 billion tons in a spoon is not a different kind of matter. It is the same matter, with the nothing taken out, down, at least, to a center nobody has ever seen into. The most extreme object in the universe is not alien. It is us, compressed. The second is about strength. We spent a long time on that crust, 10 billion times stronger than steel, holding mountains 5 millimeters tall that weigh more than every building on Earth, and yet it cracks. It has to. The pressures build, and eventually something gives, and when it does, the whole star trembles and lets go of energy that crosses half a galaxy. The strongest material in existence is not unbreakable. It holds for a very long time, then it adjusts, then it holds again. There is no version of strength that means never yielding. Even the crust of a neutron star settles when the strain gets too great, and it is not damaged by settling. It is relieved. The third is about being small. Everything we visited tonight was tiny, 25 kilometers across. A morning cycle, end to end. In a galaxy 100,000 light-years wide, a neutron star is nothing, invisible, easy to pass without seeing, and yet it bends light around itself. It slows time. It reaches across 50,000 light-years and touches the air above our heads. It forges the gold that ends up on people's hands. Nothing about its influence has anything to do with its size. And there is one more thought about scale and how easily it gets misread. It would be easy to finish an episode like this feeling small, but I do not think that is the right conclusion. A neutron star is enormously dense and enormously simple. That is the trade it makes. At that pressure, nothing can be complicated. No molecules, no structures, no chemistry. It has layers we spent a while down inside them tonight, but not one of them can hold a pattern. Nothing there ever changes for billions of years. You are the opposite trade. Almost entirely empty space, held open by a rule, and in that space around 30 trillion cells running thousands of reactions per second, maintaining a temperature, repairing damage, storing memories, and right now, turning a voice into meaning while gradually letting go into sleep. None of that is possible at high density. Complexity needs room. So the honest comparison is not small against large. It is complicated against simple. The universe can make things heavy, or it can make them intricate. It cannot do both in the same place. The staircase we walked down tonight leads to the heaviest thing that exists. It also leads away from everything interesting. You are standing at the other end of it, in the part of the universe where the emptiness was left intact, and that emptiness is not a shortfall. It is the room in which everything you have ever felt, thought, remembered, or loved has been able to happen. And the last thought is this: every heavy atom in you was delivered. The iron riding in your blood. The zinc inside the enzymes doing quiet repair work while you rest. The iodine sitting in your throat. Each one came from a star that collapsed, or from two collapsed stars that finally fell into each other after billions of years of circling. You are not observing this story from the outside. You are made of the parts that were left over. Let the numbers go now. You will not need them again tonight. Let the room come back. The weight of the blanket, the temperature of the air on your face, the particular quiet of this hour, wherever you are. Somewhere above the roof, above the clouds, above the last of the atmosphere, the sky is full of these small, heavy things. Hundreds of millions of them in this galaxy alone. Most of them dark. Most never seen by anyone. Drifting between the stars, turning slowly, cooling by fractions of a degree over thousands of years. They are not doing anything dramatic. Almost all of the time, a neutron star does nothing at all. It turns. It cools. It holds itself together. That is the whole of it, for billions of years. We went a long way down tonight, and you do not have to remember any of it. We started with a spoon of water in an ordinary kitchen, and it weighed almost nothing. Then a spoon of stone. Then metal. Then the heaviest metal a hand can hold, which was the ceiling of ordinary things, and we were still standing at the top of the staircase with everything below us. Then we went inside a planet. Then inside a star. Then inside a star that had already finished, and found something the size of a world with a sun folded quietly into it. And then, past a line that nothing crosses twice, we found the thing we came for. It is a long way down, but you did not fall. You walked it one step at a time and each step turned out to be smaller than it looked from the top. You can leave the whole staircase here. It does not need carrying, and it will be exactly where we left it if you ever want to walk it again. Let your breathing find its own pace now. Not forced, not counted. Just allowed. Imagine, if it helps, one of them turning somewhere far away. A small sphere, perfectly smooth, perfectly silent. No sound could travel there, and there is nothing to hear it if it did. Just a slow, steady rotation in the dark, going round and round and round. You do not need to picture it clearly. A vague sense of something quiet, turning, is enough. Breathe in and out. There is no rush in any of this. The star we started with took 10 million years to live and a quarter of a second to change. And then it has done nothing but turn, patiently, for 1,000 years, and it will keep turning for 1 billion more. It is in no hurry. Nothing out there is in a hurry. Whatever is waiting for you tomorrow can also wait until tomorrow. Let your shoulders drop away from your ears. Let your jaw soften. Let your hands rest where they are. There is a room. There is a bed. There is a body in it that has done everything it needed to do today and is now allowed to stop. Notice that. The bed is doing the work. You do not have to. Somewhere, an old star is cooling by a fraction of a degree that would take a century to measure. Somewhere, a crust is holding, the way it has held for 1,000 years. None of it is urgent. None of it has ever been urgent. If there is one thing worth keeping from tonight, it is not a number. It is the shape of the thing. Everything we looked at was holding itself up. The table under your hand. The rock under the table. The planet under the rock. Every one of them standing against its own weight, quietly, without being asked, for as long as it has existed. And when one of them finally could not hold any more, it did not vanish. It became something denser and smaller, and it went on holding. That is all any of it does. It holds, and when it cannot hold in one shape, it finds another one and holds in that. There is no lesson in this. The universe is not trying to tell you anything. It does not know you are here. But it is a steady thing to fall asleep next to. Somewhere far above this roof, an object that has been holding itself together since before there were people to notice is turning slowly in the dark, and it will still be turning tomorrow, and the day after, and long past that. Nothing is asking you to hold anything tonight. If you are still holding anything in your shoulders, in your jaw, in your hands, let this be the moment you set it down. Not permanently. Just for tonight. It will still be there in the morning if you want it back, and you may find you do not. Breathe in and out a little slower. The iron in your blood was made in a star. It has been traveling for billions of years to arrive at this exact place, in this exact body, in this quiet hour. It went through a supernova. It drifted through a cold cloud for longer than the Earth has existed. It sank into a forming planet and rose again and was eaten and became part of you. And now it is lying still in the dark, being warm. After everything it has been through, that seems like a reasonable place for it to rest. Let the numbers drift off first. Let the staircase go. Let the spoon go. You do not need to hold on to any of it. Somewhere very far away, something small and heavy turns once more in the dark, and then again, and then again, and it will keep turning long after tonight has been forgotten by everyone who lived through it. And that is not a sad thought. It is a steady one. The universe is holding its own weight. You do not have to help. You are made of very old material that has been through a great deal, and it has arrived here, in this room, in a warm bed, at rest. That is a good place for it to be. Breathe in and out. Let your attention go down through the bed now, slowly, the way we went down the staircase. Start at the top of your head and let it be heavy. Your forehead. The small muscles around your eyes, which have been working all day without being asked. Let them stop. Your jaw. Your throat. Your shoulders, which are almost certainly still a little higher than they need to be. Let them go down, and then let them go down again. Your arms, resting wherever they have ended up. Your hands. Your fingers, which do not need to hold anything at all now. Your chest, rising and falling on its own. You are not doing that. It was happening before you thought about it, and it will carry on when you stop. Your back, held by the bed. Your hips. Your legs, heavy. Your feet, warm and finished with the day. All of it is being carried. None of it is being carried by you. Breathe in gently. And out, slower still. The room is dark, and it will stay dark. The night is long, and there is plenty of it left. There is nowhere you have to be for hours and hours. Somewhere very far above the roof, something small and heavy turns once more in the cold, and nothing about it needs you. Let the thought of it get vague. Let it blur at the edges. Let it be a sound rather than a picture, and then let it be nothing much at all. Breathe in and out. Let the sky go on turning without you for a while. There is a lot of night left. More than you need. If you are still awake, that is completely fine. Nobody falls asleep by trying, and there is nothing here you have to finish. You can lie in the warm dark and let the words go past without following them. That is enough. That has always been enough. And if your mind wanders off to tomorrow, to the thing you have to do, the message you did not send, the conversation you keep rehearsing, let it go there for a moment, and then let it come back. It will wander again. That is what it does. You do not have to stop it. Just keep letting it come back to the dark, and the weight of the blanket, and the sound of this voice, and the small, heavy thing turning quietly, somewhere far above the roof. Nothing out there needs deciding tonight. Breathe in and out. The staircase we walked is still standing, every step of it exactly where it was, holding itself up in the dark without any help from anyone. The spoon is empty now. You can put it down. Let the room get further away. Let the edges of things soften. Let the difference between listening and not listening stop mattering. You are warm. You are safe. You are held by a bed, on a planet, in a quiet part of a very old galaxy, and every single piece of you is exactly where it should be. Breathe in gently. And out. Somewhere far away, something turns. And again. And again. It does not know we watched it tonight. It does not know anyone is here. It has been doing this since long before there was anything on this planet capable of wondering about it, and it will still be doing it long after. There is something restful in that, if you let there be. You are not required to be part of anything tonight. You are not being counted. Nothing is waiting on you until the morning, and the morning is a long way off. The blanket is warm. The room is dark. Your breathing has already slowed without you asking it to. Let the last of it go now. The staircase, the spoon, the turning, the voice. All of it can carry on without you. It always has. Every night you have ever slept through, all of it was out there, holding, turning, cooling, entirely unbothered by whether anyone was awake to notice. Tonight is no different, and tomorrow night will be no different either. You can stop keeping watch. Nothing has ever depended on you keeping watch. Breathe in and out. You have done enough today. Rest now. Thank you for spending this time here tonight. If this helped you settle, a like helps this quiet corner reach the next person lying awake, and that is genuinely the only reason it matters. And if you would like more nights like this one, subscribe, and the next one will come to you quietly, without you having to look for it. Sleep well. And may whatever you dream of be lighter than a teaspoon.